I am Engineer Nathaniel by name, and I'm happy I'm be the one taking these classes for the few time we'll have. Now let's quickly rush about the program we have for today, the topic of our this thing. Laplace transform. Now most of us must have solved issues relating to Laplace transform. First, let's get the definition. Laplace transform is a real function of f of t of which varies variable t to a complex function f of x of variable x, complex variable x. Now we have a formula. If you can check your screen, you see our formula, which it says f of s is equals to Laplace transform f of t, which is equals to 0 to infinity multiplied by f of s and e raised to the power of minus st, which we also call the kernel divided by with change of time. Now the integral will converge 1 over a portion of x plane. Hello, sir. Hello. Hello, sir. Okay. Now, one of the things we have to first of all look at is the integral will converge in 1 over a portion of an x plane. Now, when we look at it, let's say for example, e.g., RE into is greater than 0, and 2, for most of the functions except for those of little interest, that is t raised to the power of t. The function of x is determined by f of t, that's the function of time. Now we take f of x to be function of x, the capital F of in bracket open of x as function of x, and why f of t is a function of time only for when t is greater than 0. Please let us take note of that. Now look at it, the unit step function, which is a u of t is equal to 0 for when t is less than 0 and 1 for when t is greater than 0. The u of t can be approximated by the limit of a linear ramp function, which you see from my diagram on the board. Then we talk about the time shift and the rest. Now let's quickly take a little about a pulse of finite with express precise wise line function f of t as superposition of three functions. Now if you look at the table I have on the screen, you see that we have 0 to 2, 0 to minus 2, we have y1, y2, y3, then yi of t is equal to ait plus bi, or a subscript it plus b subscript I. Now this is the graph I have is with respect to time. For each interval, let's quickly just look at this example. For each interval, f of t can be expressed as the product of a linear function and a square pulse. Now, for example, L is less than T, less than 3. Now, let's look at it. Corresponding linear and square pulse functions are, if you see the formula I have, y subscript 2 of T is equal to minus 2T plus 4. And P subscript 2 of T is equal to U of T minus L, which is minus bracket U of T minus L minus U of L minus 3. So the entire function can be represented, if you're watching my screen right now, f of t is equal to y subscript 1 of t, p subscript 1 of t, plus y subscript 2 of t, p subscript 2 of t, plus y subscript 3 of t, p subscript 3 of t. Now, to look at it further, the impulse function, that's change in time, delta t. Now, an idealized mass representative sharply, you can see it from the diagram from the screen, where we have the t is equal to 0 to infinity, where t is equal to 0, then otherwise. So we also have minus infinity to infinity, where delta t is equal to 1. So, but when we look at it, we could see that the derivative of what we've just seen is what we are seeing on the screen right now, where we have 0 to 1.0, which is in change with respect to time, the limit of f of t ut is equal to limit of f of t. Then you see the graph and follow pari passu the way we just see. And gradually, this might look strange to you, but just try to follow up. We're going to do a real life example shortly. The sampling of f of t at t is equal to a, that is greater than 0, can be formulated by integral of f of t times dt minus a. Now, if you check your screen very well, you see integral 0 to infinity, integral minus 0 to infinity, f of t, then the t into t minus a multiplied by change in time, which will give us the limit to a minus dt to plus the e of t multiplied by what we just got. And if you check your screen, you see what we've achieved so far. It can be used in calculating Laplace transform of a d function or data function. So we can get everything from this place we are seeing. If you are checking your screen right now, you'll be able to see some of the formulas stated in this place. Now, these are the steps, the unit steps that we can also look at to solve the Laplace transform, which we'll be looking. This is a single exponential function that when you look at it, the single exponential function is a Laplace transform e to the power of at is equal to integral 0 to infinity, which is e to the power of minus t, then e to the power of st delta dt. This also, when we go break it down further, will give us 0 integral 0 to infinity e to the power of minus bracket a plus x multiplied by t, then the phi. This also, when we go further, it has to give us, then we have e raised to the power of minus um, a plus s multiplied by t all over minus a plus x into 0 to infinity, which give us 1 all over s plus a. That is, if re multiplied by s is less than a. These are the formulas this we are looking at. Now, I want us to show us on the list of Laplace transform pairs. We have them here on our diagram. We have the sign that is sign omega t minus u of t for f of t. Then for f of s, we have it as omega all over s squared plus omega squared. Now for the cosine, we have it as cos omega t minus u of t, which is for function of x, we now have it as x all over s squared plus omega squared. Now for the damp ramp, we have it as t e raised to the power of minus t dot u of t, which for f of x, we have it as 1 all over x plus a bracket squared. Now we can still take it for damp sign. For the damp sign under the f of function of t, we have it as e raised to the power of minus at sine omega t dot u of t, and which for the function of x, we have it as omega all over bracket x plus a squared plus omega. Now I want us to know that damping by exponential decay function causes a shift long and re-axis in the x domain. Now we're going to look at the first order time derivative. This is what is on our screen right now. If you can see very well, is self-explanatory, which we have Lagrange f of t is equals integral 0 to infinity f of t e to the power of st dt. This is integration by parts. So now when we do this, we have 0 minus f into 0 subscript negative plus x integral 0 to infinity. These are the formulas which we derive. Now for second order derivative is on the screen also. Second order derivative, we have it, let g of t equals function of time, which g of t is equals sf of x minus f0 in page 25, a week I am now, page 25 of my slides, we're looking at the second order derivative. Then we just talked about second order derivative and the nth order derivative, which is Lang, uh, Laplace transform f of n multiplied by t is equal to x of n, x raised to subscript n or superscript n, sorry, f of s. So if you look at it, we need have an initial condition in this place, and that is why I circled it with red dot, which said minus into s raised to the power of 1 f of 0 minus plus x raised to the n minus 2 f function of 0 minus then plus plus to f of n minus 1. Now let's go to the time integral, which is 26. In 26, page 26 of my slide, we have the formula is valid only if the function is integrable. Now, only if we can integrate the function, that is where this time integral, this formula will be valid. So if you check the formula I have on the screen here, on your screen, page 26, now we could see that f of x dx is equal to integral of 0 minus to infinity f of x dt dx, which is being multiplied by the exponential superscript st multiplied by dt, and that will give us 0 to infinity u of t v of t dt. Now where u, now please take note, where u now has u of t, where u of t is equal to 0 to t f of t dx. So which implies that u prime of t is equal to f of t, v prime v prime of t is equal to e raised to e s of t, or e superscript s minus t, and which implies that v of t is equal to e raised to the power of s minus t all over s. Now what we're trying to say here, from the formula above, where you see your ut, you try to inculcate the ut into that place, and we'll be able to achieve what we just achieved by having that v, which implies that v of t is equal to e, to the power of s minus t all over s. Then coming down again, we have the Lagrange of f 0 to t f of x dx. Then this is equal to u of t v of t, which is 0 to infinity, minus integral 0 to infinity u prime of t v of t dt. Now that brings us to the next line, which we have that 0 to infinity f of x dx, that is e raised to the power of st minus st all over minus x. Don't forget that we got this from the second line of on this page 26, where we have v of t equals e raised to the power of x minus t all over minus x, e raised to the power of x minus t all over minus x. So we'll go, when we come down, we'll be able to actually get the minus 0 to infinity f of t, then which brings us e raised to the power of minus st all over s change in time. So we have 0 and 1. For finite, we have 0 to infinity, or 0 to infinity f of x dx, now multiplied by e to the power of x into infinity all over minus x, then minus 0 minus to 0 minus, which is f of x dx. So when we strike it, we'll be able to have achieved 1 there. This formula is valid only if the function is integrable, like what I just told you before. Now let's move to the next slide, page 27 of my slide, and now we look at the scaling. We look at scaling. Here we are looking at scaling. Laplace transform f of a t is equals to integral 0 minus to infinity f of at multiplied by e raised to the power of minus st dt. Now, the here we are taking at equals t prime. We are taking at to be t prime. So when we take at to be t prime, so we now have the formula will now change. Wherever we see at in the above formula, we fix there we fix the t prime there. That is why if you check the second for the second line of my page 27, you see that where we are supposed to have at is not showing the t prime because we are saying let at equals t prime multiplying and every other thing remain the same except for multiply by e raised to the power of x over a. Then the change the time now t prime all over 8. This will give us f of x all over a all over a. So if this is if a is greater than 0, so this is for the scaling. Now I want us to know that a larger value of a corresponds to a narrower function in the time domain, but a broader function in the frequency domain. The width of f of at times the width of x into x over a is a constant independent of a. Please let's note that is a constant independent of a. This the page 28 now we are looking at translation in the t and s domain. We are looking at translation in the T or S domain. Now we now have translation in the time domain. Time domain will mean when Lagrange into calibraces f into t minus a, which are brackets u into t minus a. This will give us e to the power of this will give us e to the power of ax f of x f of x for a is greater than 0. So this is what we get. And when we let's again look at the translation in the frequency domain. When we look at it in the frequency domain, we find out that f, we find that f is into x plus a, that the function of x plus a. Both relation can be proven by change of variable of integration. Please let's note that both can be done that way. Both can be done that way. Now, let us look at another one which we call um, rational function. For linear long parameter circuit with constant component parameters, the S domain expression for V of t I of t are always rational functions. That is ratio of two polynomials. Please take note of that. Ratio of two polynomials. And now if you look at my page 30, where we talk, I asked the question, why only rational function? And somebody might want to ask, why only rational function? So this is why we are talking on it on page 30. Page 30, we are talking on rational function on page 30. And if you check my formula, and I said it is a ratio of two polynomials. A ratio of two polynomials. I want to agree with you that most of us already know about polynomial before we continue this. Now, in this, we are seeing from my slide on page 30, you see that my f of x now is equals n of x all over d of x. And when we go further, we have a subscript n into x superscript n plus a subscript n minus 1 in multiplied by x raised to the power of n minus 1 plus to infinity all over b, and the same thing happens there. Now the general inverse Laplace transform is this is where we are coming to, is what we have um in our page 30, the last formula there, which we are seeing the general Laplace transform. If you get your screen very well, you should see the general Laplace transform. F of t is equal to Laplace raised to the power of L raised to the power of minus 1 with your calibrates f of t. And this will give us 1 all over 2 pi I integral 1 minus infinity to 1 plus infinity. Now this will not give us f of x e raised to the power of s ds. This involves with complex integrals. If f of s is proper, m is greater than n, rational function. The inverse transform is calculated by 1. Partial fraction expansion, 2. Individual transform. That is 4 types. Now if you look at, I'm talking from page 31. If you check your screen very well, I'm talking from page 31. Now if the function f of x is an improper, that is, if n is less than or equal to n rational function, it will be a rational function. Decompose f of x as this summation of a polynomial function and a proper rational function which are inverse transformed individually. So this is how to calculate. Now let's quickly take a look at what we have on page 32. Just don't see your screen. Page 32, we have d of x has distinct real roots. That's one. Now like if you check our formula, you see where we brought out the d of x. Now we're now having f of x from the formula we've gotten before. F of x is equal to 96 multiplied by x plus 5 bracket x plus 5 bracket open and close x plus 12 all over x multiplied by bracket open and close x plus 8 multiplied by x plus 6, and this one give us k1 all over x plus k2 all over x plus 8 plus k3 all over x plus 6. So if we go by what we've been doing so far, function of x, so we have k1 plus k2 s all over s plus 8 plus k3 s all over s plus 6. Now let's take away the 2x from the formula we have here. When we take it out, then we have 96 into x plus 5 into x plus 12 all over x plus 8 multiplied by x plus 6. Now we now have, by the time we put all together, we now have 96 multiplied by x multiplied by 5. So we now have 96 multiplied by 5 multiplied by 12 and 8 multiplied by 6. So if you are with your calculator, you should be able to have, if you do the calculation, we'll have these answers 120, which is our k1 that we do not have any value on. That is our k1. So which implies that k2 equals f of x, which is x plus 8, and k3 f of x, that into x plus 6. Now if you look at this very well, when we go through it, we find that taking the limit of everything, we now have k2 to be minus 72 and k3 48, which is equals 48. Now this continues. If you look at it now, imputing the k1 into the formula which we are coming from, and this is seen the f of x is equals 1 all over 120 all over 120 l raised to the power of 1 into 1 all over x minus 72 l raised to the power of 1 into 1 all over x plus 8 plus 48 raised to the power of 1 into 1 all over x plus 6. Now what we are solving here has been on page 35, which we are looking at now. We have the function of x equals minus 12 all over x plus 6 all over j8 and x plus 3. And but when we look at it, the steps I used in solving them or calculating them were followed until we arrive at the u of t, and the circuit shows overdamped or first order. Now don't forget what we saw on the other one and under damped characteristics. Now, the third type of solving is what you're seeing on page 36. What we are seeing on page 36, that we have it. Now, I want to let this class be assured that in our subsequent class, I'm going to bring a real questions that we're going to solve it one after the other, irrespective of the time we have. We have to actually ask to follow time to make sure that we get the solvings. But from this explanation, I believe we'll be able to get our solvings. And from our subsequent we're going to be doing real-time tests and real-time assignments on this formula. So the type 3, the d of x has repeated the root, and as we can see on page 36 and page 37, you could see the formulas, the calculations there, the K2, K3, K4, which have been solved there, that we look at very well in mathematics. And there we are introducing something like the g prime of x, which is 100 x minus. So these are what we are going to look at. So we've been able to prove and see the Laplace transform formula and how it is used in first order, second order, in complex and non-complex. Now, if we go to page 42, now you will see useful transformation pairs. I want you to note these useful transformation pairs, which we might be using subsequently. We have for f of x and for f of t. Please, let's note it very well. So subsequent time, you see us using them, and we will not be confused about them. Rather than us going back to prove them, we can just decide to pick them from here and solve with them. Now, let's talk about the inverse transform. And I think I feel our time is running out. The inverse transform of improper rational function. So if you go to page 43, we see what I was able to do there when I brought out a solution. F of x is equals s raised to the power of 4 plus x 13x raised to the power of 3 plus 66x raised to the power of 2 plus 200x plus 300x all over s squared plus 4x plus 20. So when we go through that, we have this is equal to s squared plus 4x plus 10. Now minus 20 all over x plus 4 plus 50 all over x plus 5. Now this brings us from what you see. You could see the red lines on the red lines on my slide, and showing that f of t is equal to d into t plus the delta prime t minus 10 delta t plus into minus 20 e raised to the power of 40 plus 50t. Assignment, please. If we are right with our pen, take down the following assignment. It's very, very important. Please take down the following assignment. So, question one. Question one. In how many ways can a group of 5 men and 2 women be made out of a total of 7? Are we there, please? Please, I repeat again. Question number one. Please take down this question. Question one. Let's go over it again. Define Laplace transform. Define Laplace transform and give the provings. Define Laplace transform and state the provings for Laplace transform. Question 2. F of t is equals 1 for t is greater than or equals to 0. Please solve for f of t is equals 1 for t is greater than or equal to 0. Question 3. Solve for f of t is equals e to the power of t. Is equals e to the power of t. And question 4. F of t is equals 0 to the power of n for n is greater than or equal to 1 integer. Please, let's see the proving as we go on. Please solve these equations. They are very, very vital. They are the things I have just explained. And another question I'm putting forward to you. Find the Laplace transform of sine AT and cos AT. Find the Laplace transform of sine AT plus cos AT. Find the Laplace transform of these variables I have put to you. Thank you. Please submit your assignment to hello. Please submit your assignment to safetybliss@yahoo.com. All assignments must be submitted to safetybliss@yahoo.com not later than Sunday 23:59 p.m. Not later than Sunday, this coming Sunday time deadline, the deadline for it is Sunday, and the time is 23:59 p.m. Any assignment that does not get to me before then will not be accepted. Thank you.
You pronounce the safety, please? Can you spell it for us?
Safety bliss. SAFTY @yahoo.com. Safety bliss. Sorry, subsequently I'll be adding it to my slide so that we can get the email properly. But SAFETYBLISS @yahoo.com. Safety bliss @yahoo.com. Assignment that does not get to me before then, latest 11:59 p.m. should not be submitted anymore because it will not be attended to.